Hi, I'd like to continue the discussion of planning and scheduling tasks. Sections 3.1 and 3.2 continue the discussion we started in section 2.5. Remember there we had a number of people, or perhaps computer processor cores, and we had an overall complicated job to be done. Perhaps setting the table, or more realistically, an airplane pulls up to the gate at an airport and we want to turn around the plane and get it set on the new flight as quickly as possible. The overall job was broken down into individual tasks, in this case T1 through T8. Each task has a certain number of minutes or hours required to accomplish it. There are prerequisites, so task 2 cannot be done until task 1 is completed, task 3 cannot be done until task 2 is completed, and so on. And our goal is to do this in minimal time. So assign the tasks to the people in such a way that the overall job is finished as quickly as possible. Well, let's look at several ways of assigning the tasks to the workers. Here's a more or less arbitrarily chosen way. We're going to work with a priority list in each of the three methods that we'll consider. And in the first method, the priority list is just generated by listing the tasks in order of increasing number. Not job completion time, but simply the number of the task itself. So we'll say I have a priority list T1, 2, 3, up to T8. And low number prioritization says assign a person who needs a task to do the lowest number task that's already that is ready to be done. So how does that work in this example? Here's the priority list. Here's the digraph. We're ready to begin. Person number 1 steps forward and says, I have free time. Give me something to do. We go up to the priority list and say, aha, task 1 is highest priority. Is it ready to be done? I look at the digraph and see that task 1 has no prerequisites that haven't been completed. In fact, task 1 has no prerequisites at all. And say, okay, you start with task number 1. At the same time, person number 2 comes forward and says, give me something to do. I look at the priority list and say, task 2 is next highest priority. I look at the digraph and see that task 2 can't be done yet. Person number 1 is still working, in fact has just started on task 1, and task 2 can't be done until task 1 is completed. So back to the priority list. Task 3, is it ready to be done yet? No. Task 4, is it ready to be done yet? No. Task 5, no. Task 6, no. Task 7, yes. Task 7 is ready to be started. It has no prerequisites. And so I say to person number 2, all right, you start on task 7. So now we know that task 1 and task 7 are being worked on. Task 1 and task 7 are being worked on. So actually, if you look at the times, task 1 has 8 minutes of completion time till completion time, and task 7 has 5 minutes, and so person number 2 who's working on task 7 will finish before person number 1 who's working on task 1. So person number 2 finishes task 7, comes back and says, give me something to do now. Well, I look at the priority list. Say task 2 is next highest in priority of the uncompleted jobs, but task 2 can't be done yet because person number 1 is still working on task 1. Task 3, 4, 5, 6, none of those can be done until task 1 is completed, and so person number 2 ends up getting task 8, which is at the very end of the priority list, but is the only job that's still that's ready to be done. And task 8 takes person number 2 7 minutes, so while he is working on that, person number 1 finishes task 1 and says, give me something to do. Then I look at the priority list and say task 2 is next in priority. Okay, person number 1 has already finished task 1, and so task 2 is now ready to be started. Let's find a way of organizing this information. Let's do the problem again, only let's finish it this time and do so in a way that illustrates exactly the order in which the tasks will end up being assigned. So that's done with what's called a task schedule. This is the priority list. This is the order requirement diagraph. We need both of those pieces of information to generate the task schedule. And let's just start again. We decided that person number 1 was going to be assigned task 1, which is an 8-minute job. So I'm going to put person number 1 or machine number 1 is now working on task 1, and it will finish at time 8. Cross out task 1, cross out task 1. Meanwhile, person number 2, we decided is going to end up being assigned task 7. Task 7. It's a 5-minute job, and so at 5 minutes after start time, person number 2 or machine number 2 is going to finish task 7. Alright, so now we're at time 5. What happens? Person number 1 is still working on task 1. Person number 2 needs another job, and we decided that after task 7 is completed, task 8 is the only task that can be started, and so machine number 2 is going to start on task 8 after it finishes task 7. That's a 7-minute job, and it started at time 5, so 7 minutes after that is going to be out here at 12. So from time 5 till 12 minutes, processor 2 or machine 2 is going to be working on task 8. Now let's go back here to time 8. At time 8, processor 2 is working on task 8, but processor 1 is done and needs something else to do. We decided that task 2 is next highest in priority, and that is ready to be done. And so machine 1 will start working on task 2, which is a 6-minute job, and if it starts at time 8, 6 more minutes is time 14. So between times 8 and 14, machine 1 will be working on task 2. Let's keep going. I go back to time 12 because machine 2 has now finished task 8 and is ready for another job. And I look at the priority list and say, okay, task 3 is next highest priority. I look at task 3 and say, is it ready to be done yet? No. Machine 1 is still working on task 2, which is a prerequisite for task 3. So can't do task 3. How about 4? No. 5? No. 6? No, because all of these have prerequisites that eventually feed back to task 2. And so even though machine 2 has free time, nothing at the moment is available for it to do. Nothing else can be done until task 2 is finished. And so what we'll do is on the schedule, we're going to shade idle time. There's absolutely nothing that can happen, and so machine 2 just sits there and waits for task 2 to be finished. At time 14, machine 1 finishes task 2, so it's ready to do something else, and machine 2 has been idling, and so it's also ready to do something else. So we come back out and say, okay, let's get something for machine 1 to do. Task 3 is next in priority. Is it ready to be done? Yes. Machine 1 has just finished task 2, so task 3 is available. And task 3 is a 9-minute job. If it starts at time 14, it'll take it until time 23 to be done. Task 3 is being worked on. At the same time, machine 2 says, give me something to do. In the priority list, task 4 is next. Can task 4 be done? Can task 4 be done? No. task 3 is not yet finished. Jump down in the priority list, task 5. Can task 5 be done? Its prerequisite was task 2. That's finished, so yes it can, and machine 2 gets task 5. That is a 5-minute job. Machine 2 starts at time 14, and so we'll finish at time 19. At time 19, machine 2 is ready to do something else. Back to the priority list. Task 4, no. Task 3 is still not completed. Task 6, yes. Its prerequisite is task 5, and that's finished. And so machine 2 will start working on task 6, which is a 3-minute job. If it starts at 19, it's going to finish at time 22. And that'll be task 6 taken care of. Okay, at time 22, machine 2 says, give me something to do. There's only one task left, that's 4. And I go here, and it's not ready to be done yet. Machine number 1 is still working on task 3, and so machine number 2 has to idle again. At time 23, machine 1 finishes task 3 and says, give me something to do. Task 4 is all that's left. It is now ready to be done, and so machine 1 starts working on task 4. It's a 4-minute job. If it starts at time 23, it'll finish at time 27. And during that time, machine number 2 has nothing to do, so there will be idle time here. And finally, at time 27, machine 1 finishes task 4, and the entire job is completed in time 27 minutes for the overall completion time. That's what happens with this priority list applied to the problem with this order requirement diagram. This now is the schedule that shows exactly which machine will be working on which task at which time. Here's another possible priority list. Suppose somebody tells us to use this priority list instead, where the tasks are prioritized in decreasing task number. Or perhaps we just choose this. The previous task schedule might have been more or less arbitrarily chosen, and this one might have as well. Same order requirement diagram, different priority list. Let's see what happens to the schedule in this case. You might want to pause the video and see if you can work this out, and I'll proceed here and do the example as well. Machine number 1 says, give me something to do. The highest priority task on this list is task 8. It has no prerequisites, so it's ready to be done. So we start machine number 1 with task 8 immediately. It's a 7-minute job, and so at time 7, machine number 1 will finish task 8. At the same time, machine 2 says, give me something to do. Next highest priority is task 7. It has no prerequisites, so it's ready to be done, and so we give task 7 to machine 2. Task 7 is a 5-minute job, and so that's what machine 2 is going to be working on. At time 5, machine 2 finishes task 7 and says, give me something to do. Next highest priority is task 6, but it's not ready to be done yet. Nothing along this chain has been completed. Task 5 is not ready. Task 4 is not ready. 3 is not ready. 2 is not ready. Task 1, right at the end of the priority list, is available to be started, and so that's what machine 2 does. Task 1 is an 8-minute job. Machine 2 starts it at time 5, and so we'll finish at time 13. At time 7, machine 1 finishes task 8 and says, give me something to do. but task 6, 5, 4, 3, and 2 are not ready to do because machine 2 is still working on task 1, which is ultimately a prerequisite for all of these remaining tasks. And so machine 1 has nothing to do but idle. Okay, at time 13, machine 2 finishes task 1, and so both processors are ready to do something. Machine 1 says, give me something to do. I go to the priority list and say, is task 6 ready to be done? No. 5? No. 4? No. 3? No. Task 2? Yes. Machine 1 is ready to do task 2 because task 1 has just been completed. So I assign task 2 to machine 1. It's a 6-minute job. If it starts at time 13, it will take until time 19. Meanwhile, machine 2 says, give me something to do. I go back to the priority list. 6 is not ready to be done, nor 5, nor 4, nor 3, because task 2 is still being worked on. So machine number 2 now has nothing to do but idle. At time 19, task 2 is finished. Again, both machines are ready to do something. So we go back out to the priority list and looking for something for machine 1 to do. Task 6 is next in priority, but it's not ready to be done because task 5 hasn't been completed. Next highest priority is task 5. Task 2 is finished, so task 5 is ready to be assigned to machine number 1, and it is a 5-minute job. And so if it starts at time 19, 5 minutes will be out at time 24. Meanwhile, machine number 2 says, give me something to do. Task 6 is not ready to be done yet. Task 4 is not ready to be done yet. Task 3 is ready because task 2 is finished. So machine 2 gets task number 3 to work on. Task 3 is a 9-minute job starting at time 19. 9 minutes. We'll put it out at time 28. Okay, back to time 24. Machine 1 finishes task 5. Go back out to the priority list for something for it to do. Task 6 is next in priority, and if task 5 is completed, task 6 is ready to do, so it gets assigned to machine 1. Task 6 is a 3-minute job. Starting at time 24, we'll take it out to time 27. At time 27, machine 1 says, give me something else to do. The only remaining job is task 4. Task 4 has a prerequisite of task 3, which is not done yet, and so machine 1 has to idle until task 3 is finished. At time 28, both processors are freed up. Task 4 is now ready to be finished, completed, and so we assign task 4 to machine number 1. By the way, when both machines are ready for a job and there's one job to be done, it's traditional to give it to the lowest numbered machine, machine 1, instead of machine 2. That's completely arbitrary, but that's the decision that I'm going to make each time just for consistency. Task 4 is a 4-minute job starting at time 28. We'll take it out to time 32. Meanwhile, machine 2 has nothing to do because all the remaining tasks have been done, and so it idles. And that finishes all of the tasks and therefore the entire job. our overall completion time this time is 32 minutes. And remember, on the previous example, using this priority list, we were able to finish the job in 27 minutes. Now we took 32 minutes, and so the priority list does make some difference in how fast the overall job can be completed. And in this case, obviously, then this priority list was better. Low number prioritization was better than high number prioritization. It resulted in a shorter completion time. That's not always the case. In another example, high number prioritization might have resulted in the shorter time. Let's evaluate these schedules, 27 versus 32. Think about what might be possible here. Do you agree that it's not possible to finish the overall task in any time less than 8 plus 6 plus 9 plus 4? That's a sequence of tasks that have to be done in that order. And task 2 can't be started before task 1 is completed. 3 can't be started before 2 is completed. 4 can't be started before 3 is completed. So I claim it's not possible to complete the job, no matter how many processors you have, in time less than 8 to do task 1, plus then, after that's finished, 6 more to do task 2, plus 9 more to do task 3, plus 4 more to do task 4. And 8 plus 6 plus 9 plus 4 is 27, and that's what we happen to get using using low order prioritization like this. And so in this case, not always, but in this case, low order prioritization gave the best possible schedule. Shortest time. Again, I know that just by looking, and I find a sequence of tasks in a prerequisite chain that have total time 27, so I know I can't complete the job in any shorter time than that. For high order prioritization, we got a completion time of 32. Let's do our actual minus optimal divided by optimal to convert to a percentage beyond optimal. So 32 minus 27, what we got with this prioritization, minus the best possible divided by the best possible, convert to a percentage. And if you work that out, it's approximately 19%. And the meaning of this is longer than optimal. By using high order prioritization, we got a completion time that's 19% longer than the best possible solution. You ask yourself, well, would that be good enough? If this is what we came up with first, would that be good enough? Maybe, maybe not. I mean, it's not terrible. It's not like it takes 3 times as long as what our best possible solution could be done. But in a competitive business like the airline industry, if Delta, for example, were using 19% more time, turnaround time at a gate than another airlines, that in itself would probably not be a good thing for Delta, because the airline industry is very competitive in terms of profit margin. All right, what's the theory behind this? How can the best task schedule be found? How can we go about choosing the priority list so that it results in the best schedule? One way would be brute force method. Just list all possible priority lists, build the schedule for each of them like we did. We've done 2 examples here, and then choose the best schedule. Let's say, okay, this is a brute force approach. How many priority lists could there be? If there were n tasks, we just did an example where there were 8 tasks. What if there are n tasks? I want to say, how many priority lists are there? Well, remember this business of successive choices? The first choice would be, okay, how many options do I have for what's placed first in the priority list? And the answer is there are n tasks. I could put any of those at the beginning. Once I've done that, how many choices for the next slot in the priority list, the second slot in the priority list? I've used one. I have n minus 1 left over. How about for the third slot in the priority list? N minus 2 choices there, and so on down to next to the last slot on the priority list, 2 choices, and then the remaining task is going to be put in the last slot in the priority list. And this is n factorial, remember. And remember how fast the factorial grew. So 3 factorial was 6, 4 factorial was 24. Even in our example that we've been considering so far with 8 tasks, 8 factorial is an extremely large number. And so I would have to do a huge number of possible schedules before I could consider choosing the best one. For 8 tasks, the problem is already much too large to be done by hand, and by the time you get up to 15 or 20 tasks, the problem is also too large probably to be done by computer. So brute force is not a very attractive way of doing this type of problem. So let's see if we can find a better way of generating the priority list rather than brute force. That's called optimal task scheduling. And we'll hope for an algorithm that generates the best possible schedule. If we can't get that, we might have to settle for a heuristic algorithm, remember, which is one that gave hopefully a good schedule, not necessarily the best possible. But in terms of choosing a good priority list, which task to be given highest priority, we've already discussed this question. What characteristics of a task in an order requirement diagram indicate that it should be given high priority? And if I had not said anything about this situation and you had not heard of it, and I ask you this question, you'd probably say task 1 because it's a bottleneck. It has to be done before lots of other things can be done. In fact, in the last section, section 2.5, we talked about the critical path, and more precisely, task 1, giving task 1 high priority would be a good idea because it's at the beginning of a critical path. Okay. So this method then is going to be called critical path scheduling. Works like this. You have the order requirement diagram in front of you. You're trying to generate the priority list that you'll then use to generate the actual schedule. Critical path scheduling is a way of generating a priority list from the order requirement diagram. Choose any task at the head of a critical path. So there might be just one critical path, or if there's a tie, then there might be multiple critical paths. Choose a task at the head of a critical path. Put that at the beginning of the priority list and then delete it from the diagram. And go back and cycle through number 1, number 2, number 1, number 2 until you've used up all of the vertices in the diagram. And as you make choices in step number 1, that will be generating the priority list in the order used. The way to see this, of course, is by an example. Let's use this diagram as an example. All right, there are 10 tasks here, and the diagram illustrates various completion times and various prerequisites. The algorithm said, find the critical path. All right, I look at it and say, what is the longest chain in terms of sum of completion time that I could find here? And it might take a little bit to do that. It's probably going to involve the 36. That's a big number. There's a tie for 14s here, and then 14 is here, and that's more than the 4 plus 6. So it turns out that the critical path then is T1, either T2 or T4, it doesn't matter. So I'll say T2 and then T3. That has length 14 plus 14 plus 36, and that's more than any other path that you can find. All right, step 2 of the algorithm said the task then that's at the beginning of the critical path will be given highest priority when we get to the priority list. In other words, this is going into the priority list first now. And the algorithm says, okay, you've already chosen task 1 where it's going to go, so go ahead and delete it and any associated edges from the digraph. And so here is the result once this task 1 is gone, and now you just repeat the process and start anew and say, okay, what is the critical path here? And I think 36 again is large, so feeding back through here, if I start at T5 and go to T6, then 4, then 3, that's going to be my new critical path. The task at the head of that critical path is 5. It's back here. And so that and any associated edges are going to get deleted, and I'll continue the process. Once I delete task 5, the digraph looks like this, with a critical path of T6, T4, T3. So next priority will be T6. That gets deleted. Now the critical path is either T4, T3, or T2, T3. Either one would be fine. I'll use T2, T3. And T2 is at the head of that, so it gets deleted. Now the critical path is T4, T3. T4 is at the head of that. Delete it. Now the critical path, okay, think carefully here. Here's a chain of 3 tasks, but the total completion time, 4 plus 4 plus 16, is still less than 36. And so the critical path for this digraph is simply T3 by itself. And of course task 3 is at the head of that path, and so it goes into the priority list next and gets deleted. Now the critical path is T8, T9, T10. Task 8 goes into the priority list and gets deleted. The critical path now is T9, T10. Task 9 goes into the priority list and gets deleted. The critical path now is either T7 or T10. I'm going to choose T7 as the lower numbered task, but that's an arbitrary choice. It would have been fine to say T10. T7 is next highest priority and gets deleted. And finally, we're here. There's only one task left, and so just that task is the critical path here. And that's next highest priority. Okay, now we've gone through the sequence of steps 1, step 2, and the algorithm said prioritize the tasks in the order chosen above. So I go through and use the tasks circled in the order in which I circled them. So task 1, 5, 6, 2, and so on in that order. So let's list them here. We ended up deciding that task 1, task 5, task 6, task 2, task 4, task 3, task 8, task 9, task 7, and task 10. In that order is the priority list that resulted from critical path scheduling. Okay, let's go ahead and generate the resulting schedule then. And I'll go through this example a little faster because we've done several of these before. You might want to again pause the video and work out the schedule for this priority list and this digraph. What happens is now that machine 1 starts task 1, it's ready to be done with a 14-minute completion time. Machine 2 starts task 5, 4-minute completion time. Then machine 2 works on task 6, with a 6-minute completion time. Then machine 2 works on task 8, that's ready to be done, with a 4-minute completion time. Notice that tasks 2, 4, and 3 were not ready to be done because task 1 is not finished yet. Okay, at time 14, then task 2 is next highest priority and it's now ready to be done. That's a 14-minute job. And machine 2 gets task 4, which is now ready to be done. And it's also a 14-minute job. Both processors are ready at time 28. Next highest priority is task 3, which is ready to be worked on. And it is a 36-minute job, so that's going to go all the way out till time 64. At time 28, machine 2 can start task 9. It's a 4-minute job. And then task 7. It's a 16-minute job. And then task 10 is also a 16-minute job. So actually they will finish at the same time at time 64 and the entire job will be completed. And so this is the completion time. Okay, is this good? Well, I look at the schedule and say, would there be another way perhaps to get this job done faster? Okay, I don't think so now because notice that there's absolutely no idle time. The two processors are busy the entire time until 64 minutes have passed. So if you think about it, there's no possible way to get the job done faster than 64 minutes with only two machines. They're already working full-time as hard as they can for the entire 64 minutes. So this happens to be the optimal completion time. And part of the reason is, remember, we worked pretty hard to generate this priority list with critical path scheduling to put tasks that are bottlenecks early in the priority list so that they got done soon, so that the remaining tasks then could fall into place. So then the question becomes, well, okay, critical path scheduling in this case gave the optimal completion time, the schedule with optimal completion time. Does that always happen? If you use critical path scheduling, do you always get the best schedule? Let's look at another example, try and decide whether that would be the case or not. Here's kind of a strange looking example. Here's the order requirement digraph. We want to generate the priority list using critical path scheduling. So let's do that on just one page now rather than consecutive slides. Initially, the critical path, so I want to involve this 10 because it's at least as big as these, or it's as big as these 10s. Then I can get any of these 3s and then this 1. So it seems pretty clear that task 1 is going at the head of the priority list because a critical path, for example, would be T1, T8, T12. Task 1 then is already on the priority list. And I look at the new digraph and say, okay, any of these, task 8 to 12, 9 to 12, 10 to 12, or 11 to 12 would be next highest priority. In other words, 8, 9, 10, or 11 are at the head of a critical path at this point. And so task 8, for example, could go in. Once that's done, then task 9 to 12 to task 12 would be the critical path, and task 9 is at the head of that, so it goes in the priority list. Then 10, then 11. At this point, the critical path is T11, T12. So that's gone. Now, with tasks 1, 8, 9, 10, 11 all gone, what's the critical path? There is task 12, there's task 5, task 6, and task 7, all having 10-minute completion times. And so each of these, just by itself, would be a critical path. So I'll choose task 5 since it's the lowest number, arbitrary choice. Then task 6, then task 7, and then task 12. And finally, tasks 2, 3, and 4 remain. They're each 1 minute long, and so a critical path is just task 2 or task 3 or task 4 by itself, and I'll use them in task 2, and I'll use them in that order. And say, okay, here is the priority list that results from critical path scheduling, and proceed to build the schedule using this priority list and this order requirement digraph. Suppose I have 4 machines, just for the sake of variety, and let's go ahead now and generate the schedule. So if you remember the priority list from the previous slide, task 1 was highest priority. It's a 1-minute job. And then machines 2, 3, and 4 all need something to do. And way down in the priority list were tasks 5, 6, and 7. None of the rest of the information is, none of the other tasks are ready to be done. You might want to look back at this priority list. And so I'm going to start machine 2 on task 5, machine 3 on task 6, machine 4 on task 7, and those are all 10-minute jobs. So machine 1 gets done fairly quickly, and so next it's supposed to be working on things like T8, and when it gets that done, T9, T10, and so on. So that's what's going to happen. Those are all 3-minute jobs. And so T8 T8 happens next, then T9, and then T10. So at time 10 minutes, all the processors are ready for another task. Looking back at the priority list, T11 was next in priority, and it's now ready to be done. It's a 13-minute job. Meanwhile, if I look back at the priority list, T2, 3, and 4 are at the end of the priority list, but they're next. They're the highest priority tasks of the ones that are not yet completed. Oops. Let's go back here. So T2, T3, and T4 all get assigned as 1-minute jobs. At time 11, then, machines 2, 3, and 4 are ready for another task, but the only thing remaining is task 12, and it can't be done yet because machine 1 is still working on task 11. So nothing to do but idle. Now at time 13, machine 1 finishes task 11. Task 12 is the only thing remaining, and so machine 1 will start task 12, and that's the biggie. It's 10 minutes, and so out to 23. And that's the last remaining task, so these machines have nothing to do but idle. Notice all of this idle time. This job will be completed in 23 minutes then, but it looks like a fairly inefficient schedule. This is the schedule that resulted from critical path scheduling, completion time 23. And I won't go through it, but it is possible to find another schedule that looks like this, which has completion time of only 14. This schedule did not come from critical path scheduling. It came from brute force, just trying lots and lots of different priority lists until one works. Or maybe you might look at it and see that it might be a good idea to have the other processors doing tasks 2, 3, and 4 while processor 1 is doing task 1 to avoid the situation we saw here where machines 2, 3, and 4 worked for a while, but then were not able to do much more because of a bottleneck that was then created. If we assign tasks 2, 3, and 4 to machines 2, 3, and 4, then the machines can kind of be working in parallel, and this problem obviously has a lot of parallel structure. But the important point here is better schedule than was found using critical path scheduling. And it only takes one counterexample to disprove something. So our guess might have been that critical path scheduling would find the optimal schedule. It did not. So critical path scheduling does not always find the best schedule. That's unfortunate. It will seem like a very intuitive thing to do, and what we've just discovered is that critical path scheduling is a heuristic algorithm for task scheduling. It tends to find a good solution, better than we probably would stumble on just using some random scheme, but it is not it's a heuristic algorithm rather than the best possible one. Might there be another way of finding the best possible schedule other than brute force? And the answer turns out to be no, not an efficient way. And so task scheduling is going to fall in the category of a hard problem, just like Hamiltonian circuits and the traveling salesman problem. There is no known efficient way for finding the best possible schedule for an arbitrary order requirement digraph. Critical path scheduling is a heuristic algorithm for hopefully finding a good schedule. Thanks.